Hi guys, my name is Ashrith, and in this lecture we're going to look at modulo arithmetic. So if you're a high school student who is preparing for math olympiads or a college student who has a math major, this lecture is for you. We are going to do a couple of things here. We are going to first look at the theory, and then we're going to look at few problems and few example problems, and the level of the lecture is going to be a bit high as modulo arithmetic is not an easy concept, and at the end of the class maybe we're going to solve up to 9 or 10 problems, and the last problem is going to be from math olympiads which came in different countries and different areas where this might help you a lot. So what's modulo arithmetic? So I'm going to just define what my modulo arithmetic is, and then I'm going to explain. So if two integers a and b are said to be congruent modulo m, if a and b have the same remainder, then we call them it is congruent to modulo m. So it is fine if you don't understand this, because if you're learning it for the first time, yes, you wouldn't understand. So let me take two numbers a and b, and I am saying that I'm going to construct a division algorithm with these two. So a equals to mq1 plus r1, and let us say b equals to m into q2 plus r2. So observe here that I am dividing a and b by the same number, which is m. I'm dividing, so in the division algorithm, m here, q is so one second. So dividend, so for people who have no idea what division algorithm is, dividend equals to divisor into quotient plus remainder. So here m is my divisor, a and b, m is my divisor, a and b are my dividend, and q1 comma q2 are my quotients, and my remainders are r1 comma r2. So now when I construct a division algorithm, I get it in this form. So now what if so this is a case in modular arithmetic if r1 equals to r2. So here I'm just writing r1 instead of r2. So now I have b equals to mq2 plus r1 and a equals to mq1 plus r1. So now let me take this as equation 1 and this as equation 2. I'm gonna subtract both of them. 1 minus 2, you get a minus b equals to m times q1 minus q2, and you can see the r here and r here are gonna get subtracted because both are equal. And I'm gonna write q1 minus q2 as some capital Q. So a minus b equals to m into some random quotient. I don't care about the quotient here, so I can write this as a equals to m q plus b. So if I have two numbers a and b such that it leaves the same remainder when it is divided by some anonymous digit or a number which is m, then I say that a equals to mq plus b. The only thing here is the remainders are same when you're dividing by a number m. So an integer m, you can take it as integer or number, whatever you want. So I get a equals to mq plus b, or some people just write it like this. So with this, for modular arithmetic, I write in the form of I'm writing a minus b equals to mq in a different form. So in a different form, I write a congruent to b mod m. So here, so in modular arithmetic, I do not care about the quotient when a minus b is divided by m. I only need the divisor which is dividing A and which is dividing B, and the remainder what we're getting. So A equals to A congruent to B mod M. So if if someone gives you A congruent to B modulo M, then you can write it as A minus B equals to M into some arbitrary number, which is the quotient. What I do not care about is Q. So if you have A minus B equals to MQ, then you can write it as A congruent to B mod M. And if you're given A congruent to B mod M, and then you can write it as A minus B equals to MQ. So this is a really simple concept where many people will get confused, and for some people it's going to be a tough concept. In general, it's a not so tough, not so easy concept. So A congruent to B modulo M can be written as A minus B equals to MQ. So this is just a different notation. This is just a different notation. So in geometry, so if you have idea about geometry and about congruent triangles, so I have a triangle here like this and another triangle here. So this is maybe 30 degrees, this is 30 degrees, this is 45 degrees, this is 45 degrees, and this side equals to this side. I say that with ASA congruency that both of these are equal. Or we say that the triangle, so if I name the triangle A, B, C and D, D, E, F, oh sorry, my bad, D, E, F, I say that the triangle ABC is congruent to the triangle DEF. So in the same way, the numbers here A and B are not equal. So in geometry we say that congruency is equal, but in modulo arithmetic or number theory, when if A is congruent to B, that implies it leaves the same remainder when M divides A and B. And then if A congruent to B mod M, so in this case if I say A not congruent to, so if A and B does not leave the same remainder when M is dividing A and B, then I can write A not congruent to B modulo M. So if you haven't understood totally with this theory, I'm gonna do some basic examples through which you can understand properly. So before we go to the example, just give me a second. Yeah, so sorry guys for interrupting. So let me take few examples. So examples. So if I have a number 28 congruent to 3 mod 5. So I was given an example, I have given you this. So just start thinking. So I'm asking whether this is true or false. Whether this is true or false. So just pause it guys and start solving it. And if you pause the video and start solving it, I want you to try on your own first, which develops your mental ability plus problem solving strategy also. So I'm going to solve it now. So 28. So I'm just writing, this is A, this is B, and this is M. So A minus B equals to MQ. That implies 28 minus 3 equals to MQ. 28 minus 3 equals to 5 into Q. 25 equals to 5 into Q, which is true because 25 is a multiple of 5. So if you wouldn't want to do all this, you can, this is a simpler method, 28 congruent to 3 mod 5. Just send 3 this side. So assume if so you have 28 congruent to 3 modulo 5. So assume it just like a equal to sign, 28 equals to 3, and when you send 3 this side you get 28 minus 3 equals to 0. So what you get here is when you send 3 this side you get 28 minus 3 congruent to 0, modulo 5. 25 congruent to 0 mod 5, which is true because 5 divides 25. So I'm gonna give another example. This is example number 1 and the example number 2. The example number 2, 40 congruent to 1 modulo 13. So I'm just writing a couple of examples. 3, 68 congruent to 4 mod 16. 72 congruent to 0 mod 8. So what so I'm just writing, so I'm just sending one this side, just send one this side, assume the congruent sign which is the 3 slashes as equal to and send one that side. So you get 39 congruent to, so 40 minus 1 is 39 congruent to 0 mod 13. Yes, 13 divides 39. 68 minus 4 is 64. 64 congruent to 0 mod 16. Yes, it is. And 72, because it's already congruent to 0, we can you can directly check whether 8 divides 72 or not. Congruent to 0 mod 8, because 8 into 9 is 72. So now we are going to look at some properties of congruency. So after the properties of congruency, we'll be going to solve some 8 to, I think we're going to solve 11 questions, and few of the questions have come in the previous questions, like previous Olympiads like AIME, AMC, the Indian Regional Mathematics Olympiad, RMO, and others also like Balkan Olympiads. So I'm going to take some questions. So before we start the properties of congruency, let me just keep the heading once. So before we start the properties of congruency, so after each part, I usually give some 3 to 5 minutes of break. So you guys can pause the video or forward the video, or you can just take a 3 minutes break, by which you can understand the next topic pretty much easier. So if you usually give a break, you can understand it a bit nice. So I'm gonna give a 3 minutes break, and if you don't need any break, you can obviously just forward this part, and I'm going to start exactly in 3 minutes. Oh, okay, guys. Now we're going to start. So I hope your brain is fresh and good so that we can start properly. So let me go through the properties of congruency. So if I have A congruent to B mod M, so I'm going to write this A congruent to B mod M, and I have B congruent to C mod M, then that implies that I can write A congruent to C mod M. So first I'm going to tell two proofs. So one is visually and one I'm going to write it afterwards. So just remember that A when A and B when M is dividing A, it leaves a remainder R1, and when M is dividing B, it leaves a remainder R1. So now, so we say that the remainder here is R1 for A and B. For A comma B, the remainder is R1. So now the remainder is same for B. So when M is dividing B, we get a remainder R1. So here, because they have given us that B congruent to C mod M, that implies that M, when M is dividing C, it leaves the remainder R1. Because we already know that when M is dividing A, it leaves a remainder R1. So from the first one, we know R1 as this, and from the second one, from the first one, we know this, and from the second one, we know this. So we can directly make a relation between these two as A congruent to C modulo R1. M. So now I'm gonna derive it also, a proper derivation or a proper proof. So A minus B equals to M into some capital Q, and B minus C equals to M into some small q. So I know this thing from here and this thing from here. I'm gonna add both of them. I get A minus C equals to M into q plus small q. I'm just gonna write it as some k. So A minus C, so with this I can write A congruent to C mod M. So this is a proper proof, and I hope you have understood this. And let's go to the second property. So for modern Olympiads for high school and basic college math, you just need 5 properties which has to be known and which is important. And the second property is if A congruent to B mod M and I have that C congruent to D mod M, that implies I can write A plus or minus C congruent to B plus or minus D mod M. So proof writing is also really important for Olympiads. So with the proof writing, you can learn a lot. So if you have not paused your video and just pause it right now and start solving it. Start solving and try to prove that A plus C is congruent to B plus D mod M and A minus C is congruent to B minus D mod M. And after you pause it and start solving, then I'm gonna resume. So I'm gonna write the proof here. So I hope you have paused it right now. If you haven't still, go pause it now. So I'm just writing A minus B. So I'm going to write it in different form. A equals to B MQ plus B and A plus sorry, one second. And C equals to MQ plus D. So I'm gonna add these two. Case 1 I'm gonna add A plus C minus B minus D equals to, So this is mq1 equals to m into some q2, q plus q1 equals to q2. I'm just adding here, you get b plus d, and you just send it that side. So I'm taking this as one and this as another. I can write from here that a plus c congruent to b plus d mod m. So observe. So here's a plus here. So observe, I'm writing. So if I have something like a minus b uh, equals to mq, I write it as a congruent to b mod m. So here my a is a plus c and my minus b as minus b minus d. And if you want to try something else also, you can write the same thing as a minus d congruent to b minus c mod m. uh, I'm just sending c this side, plus c becomes minus, and d this side, plus d plus I mean, if I send c this side, plus c becomes minus c. So we get something like this. So assume the congruent sign is just equal to, and you can play with the numbers. Send it this side and that side. And similarly, really similarly, you can do it for a minus c congruent to b minus d mod m. So it's a really similar thing. I'm not gonna prove that obviously because uh, so the third one, if a congruent to b mod m and c congruent to d mod m, so I can write ac congruent to bd mod m, and then I'm gonna write the proof. As you know, just pause it and start trying. So I have that a equals to b some 1 second, equals to mq plus b, and c equals to mq1 plus d. So I'm assuming this as equation 1 and this as equation 2. I multiply the equation 1 into the equation 2, which gives us AC equals to mq plus b into mq1 plus d. So I'm just going to multiply everything now. AC equals to m squared q into q1 plus mqd plus mq1b plus bd. So assume all this, you can take m common out of all these, which is unnecessary. You can just take m into some capital Q. So I get AC equals to m into some capital Q plus BD, and I have AC minus BD equals to m into some capital Q. From here, I can write AC congruent to BD mod m, and that's it. A really simple proof. So whenever you're multiplying something like mq plus b and mq1 plus d, it's obviously general fact that the only possible case where you do not have an m is b into d. Simple. So this is the third property, and let's go to the fourth. If same again, we're writing the same statement 1,000 times. A congruent to b mod m and c congruent sorry, yeah, we haven't written it 1,000 times. I'm just joking. Yeah. So I can write that a power n is congruent to b power n mod m. This is a powerful statement. So if you're writing my notes, well and good. It's a really powerful statement. You're gonna use this in kind of like every question, man. You gotta you got to know this property like pretty well. So A congruent to B mod M, and then A power n congruent to B power n mod M. Then, so I'm going to prove this. So I want you to try this again. So just pause the video and try. A congruent to B mod M can be written as A equals to mq plus b. Square it. So I'm just squaring it now. So okay, fine, just take it to the power n. Just take it to the power n. A power n congruent to mq plus b into mq plus b into mq plus b into mq plus b, so on till mq plus b, where all this is n times. So observe one thing. So as in the previous question, I have told you that here there's only one possible case in this question. In this property, there's only one possible case, b into d, which gives us no m. So how do we get no m this? So if we multiply b into b into b into b and so on n times, we get b power n. But in case you take b into m, you get m. So here, whenever you get some m into b cube or something, you can just take m common, b cube plus b square, whatever it is. You can just take m common and write it like this. That's what we don't want. We don't want, so this is going to be a quotient. We do not want a b in the quotient. So if you don't want the b in the quotient, then you can just multiply b into b into b into b into b, which gives b power n. So I can write a power n equals to some m into q plus b. So from this I can write a power n congruent to b power n mod m. So I'm going to give some example now. Example, this is a place where you need some proper example. So if I have 5 congruent to 1 mod 4. So why do you want to take 1? Fine, I'm going to give a better example. Okay, fine. 19 congruent to 3 mod 16. I can write 19 square congruent to 9 mod 16. What's 19 square? I don't remember. Yeah, okay. So if I was already, I know that. So fine. So if you have a number, so if they see what is the remainder when 361 is divided by 16, and if you know, unlike me, I don't remember 19 square. So if you know that 361 is 19 square, so what you do, so you want to find 19 square congruent to x mod 16. I don't know what my x is, so just ignore. So first what you're gonna do is 19 congruent to 3 mod 16, and then square it on both sides. 19 square congruent to 9 mod 16. Then you can write this as 361 congruent to 9 mod 16, because 19 square is nothing but 361. So that's really simple. So you can do that for cubes, for power 4, 5, 6, 7, power 8, power 10, so on. So our last property, where it's a kind of important property, but not that important property like the previous one, but it's kind of important. AC congruent to BC modulo M, and the GCD or the HCF of C comma M is 1. Then I can write A congruent to B mod m. So if the GCD of c and m is 1, I can just cancel the c like this and I can get this. So now I'm going to prove it. So I'm just going to write it in the division algorithm stuff. AC equals to m into some q plus bc. So oh sorry, I can just I'm just going to write it like this. I'm just taking c common, sorry, c common into a minus b equals to mq. So when m does not divide m, see we know that m does not divide c. M m does not divide c because the GCD or HCF of c and m is 1. So that implies that m divides a minus b. From this, because m does not divide c, m has to divide a minus b because the LHS must be equal to the RHS. So I can say a minus b equals to m. And with this, I can say a congruent to b modulo m. So these are some 5 properties, guys, where these are really important properties of congruency. And if you want these notes, you can just go to the description below and find the link of the. I think you'll have a Google Drive link or something. So now we're gonna see some questions. We are gonna see some questions. Question number 1. So n is a natural number. N is a natural number. So find the possible remainders when n square is divided by 2, 3, 5 and 6. So I'm not gonna tell it right now. I want you to try it for some time. I'm gonna wait for 2 minutes. So if you want longer than 2 minutes time, it's fine. It's totally okay. I'm not. There's nothing wrong in that. So I want you to pause the video, or if you're fine with 2 minutes, then just play the video and wait. So I'm gonna start after 2 minutes. Okay, I think the 2 minutes is kind of done now. So for the homework, So I'm gonna solve 5 questions now, and I'm gonna give the other. I'm gonna solve 6 questions now, and I'm gonna give the other 5 questions as homework, and the solutions of the questions is also gonna be in my description. So if I solve 5 questions, 6 questions now, and if I want you to solve the rest 6 questions, I mean 5 questions, it will be like a practice work for you too. So let's start. So so every number can be of the form 2m or 2m plus 1. So just take something like uh okay, let's say take the series of natural numbers. This is 2m plus 1 where m is 0. This is 2m where m is 1. This is 2m plus 1 where m equals to 1. So 2 into 1 plus 1 and so on. So every number can be written in the form of 2m or 2m plus 1, or it can be written as 3m or 3m plus 1 or 3m plus 2. So if you write 3m plus 3, I can take 3 common and just write it as 3 into m plus 1. I'm going to write this as 3 into q, 3q or 3m. So every number, and then 5 can be written as 5m or 5m square, 5m plus, sorry, 5m plus 1, 5m plus 2, comma 5m plus 3, comma 5m plus 4, and then 6 can be written as 6m plus 1 plus 2 plus 3 plus 4. So now I'm going to solve these 3, and 6th question will be your homework, a very simple homework. So now I'm going to write it as n. So n equals to 2m comma 2m plus 1. So I'm going to try to solve it in a different way. So n square, okay, n congruent to 1. So n equals to 2m, fine. So I'm writing n, my natural number, 2m. So 1 second. So I'm planning to try to tell in a different way. Fine. 1 second. So I'm going to write n equals to 2m comma 2m plus 1. So n square equals to 4m square. So the remainder when n is divided by 2. So I have two cases here. So n square equals to 2m plus 1 whole square, and I get n square equals to some 2k plus 1. So I can get it is 2m plus 1. So if I want the remainder, I get 1 and 1. So when 2 is divided by n, when 2 is divided by n square, so in the first case you get a case of 0, the remainder is 0. In the case of the second, you get the remainder as 1. So when you have, so there's something different what I want to say. So if I have something like 2m plus 1 and I want to find the remainder when it's divided by n square, just square the 1 here. So when what is the remainder when 3m is divided by n, then if n is of the form of 3m, then I can I can say it's obviously divisible by 3. If n is in the form of 3m plus 1, then n square will leave a remainder 1 when it is divided by 3. When n is in the form of 3m plus 2, then n square leaves a remainder 4, which is nothing but 2 square. So n square will leave a remainder 1. So uh, so guys, I think you have understood. So you can just square this time. So n equals to 5m. N square is obviously divisible by 5. If n square equals n equals to 5m plus 1, the remainder is 1 square, the remainder is 2 square here, the remainder is 3 square here, the remainder is 4 square. A really simple concept. So now I'm gonna just write the questions. So the rest 5 questions what I want you to try. Question 2. uh, so I'm just writing all the questions at a time. So if show that sorry, this is uh, I'm writing a couple of questions. I'm gonna write 5 questions. If 9 divides a square plus b square plus c square, then prove that prove that 9 divides a square minus b square, or 9 divides b square minus c square, or 9 divides c square minus a square. This is the question number 2. Question 3. Show that there exists no integer so until I write the next 3 questions, you can just start solving the fourth, the second question. Integer n such that the sum of the digits of n square is equal to 2021. Question 4. Show that there are no integers ABC, A comma B comma C, such that a square plus b square minus ac equals to 6. And at the end, the question number 5. If two numbers are divisible, two numbers in the form uh, m square and if two numbers divide so I'm going to write a different question. This one is an easy question, so I'm going to give a bit tougher question. Show that the sum of the square of two whole numbers is divisible by 3 is divisible by 3 if and only if each of them each of them is divisible by 3. So for these four questions you might take at least some 15 to 20 minutes, but I'm not going to wait for you for 15 to 20 minutes. So I just want you to pause the video and start solving it. So I'm going to write the solution 2 here. Solution 2. So if, let's see the question. So if 9 divides a square plus b square plus c square, then prove that 9 divides a square minus b square, or 9 divides b square minus c square, or 9 divides c square minus a square. So now, so let us try to take the possible cases when a number, when a number is divided by 9 square. So when there's a number, and when a square of a number, so I should try to find a square congruent to mod 9. So here x can have many values. So here I need to find what are the possible values of x. So if a square is in the form of 9m, if a equals to 9m, a equals to 9m plus 1, a equals to 9m plus 2. So here I can write 9m plus 8 as 9m minus 1. See, the sequence is 9m plus 1. So if I subtract 1 from 9m, which is 9m minus 1, which is nothing but 9m plus 8. So I can write 9m plus 8 as 9m plus or minus m. I can write 9m plus 7 as 9 plus or minus 2. I can write 9m plus or minus 3. A equals to 9m plus or minus 4. So these are the possible cases of the value what a can be. So we need to find a square. A square equals to 9q. A square equals to 9q plus 1. A square equals to 9q plus 4. A square equals to, in the form of 9q, a square equals to 7, 9q plus 7. So here I have the possible remainders 1, 4, 7, and obviously 0. So when 9 divides a square, so the possible remainders are 0, 1, 4, and 7. These are the possible remainders when some number is dividing, when 9 is dividing some number. So let me write the possible. So I know that a square plus b square plus c square congruent to 0 mod 9, because I know that 9 divides a square plus b square plus c square. I can write this thing. So so with this I can say that, so in this is a hit and trial now. It's a hit and trial. We need to take some possible cases such that a square plus b square plus c square equals to, so we need to take some possible cases such that a b c are these numbers and this is equals to, so case 1, a square plus b square plus c square equals to 0. Obviously 9 divides 0. So there's one possible case, 0 0 0. If a square plus b square plus c square equals to 9, then we can have some number of possible cases, like 117 is one possible case and 441 is one possible case. So you can check, there's no other possible case. If a square plus b square plus c square equals to 27, I mean 18, there is another possible case, 477. You can see 4 plus 7 equals to 18. So these are the four possible cases. And then see, a b c can be any of these, a b c, a b c, a b c. So now observe, Now they're asking a 9 must divide a square minus b square, or 9 must divide b square minus c square. You can observe that, I'm just zooming in a bit. You can observe some any two. If any two numbers, if any two numbers are the same, then a square minus b square equals to 0. So if these two numbers are the same, it leaves a remainder 0. So this leaves a remainder 0. Even this leaves a remainder 0, because a square minus b square is equals to 0, because the 9 divides a square minus b square. So 1 minus 1 equals to 0. 4 minus 4 equals to 0. I mean 4 square minus 4 square equals 0. 7 square minus 7 square equals 0. So this is what we had to prove, that 9 divides something. So we have got 4 possible cases, and we have showed for each of the possible cases this is true. Then we are done. That's what we have shown. So now let us look at the third question. Show that there exists no integer n such that the sum of the digits of n squared is equals to 2021. Fine. It's a really simple. This one is a really simple question. So any number can a square congruent to, again, x mod 3, because they're asking it's not divisible, if it's divisible by so okay, fine. uh, so fine, let me just tell you a simple concept. So if I have a number a square and I want to find the number of possible remainders when I'm dividing it by 3, so the possible remainders are when a square is 3m, when a square is 3m, when a square is 3m plus 1, and when a square is 3m plus 2. As in the first question I have told, the possible remainders are, this is 0, this is 1 square, and this is 2 square. So the remainder is 1 here, and the remainder is also 1 because 2 square equals to 4, and 4 has the remainder 1 when it's divided by 3. So when a square, when 3 is dividing a square, then the possible remainders are 0 and 1. So in this question, they have given the sum of the digits of n square is 2021. So the sum of the digits is 5. So 5 is nothing but 3m plus 2. So by here we have got that a square can be in the form of 3m or 3m plus 1, because it leaves the remainder 0 or 1 when it is dividing by 3. So we can say, we know that the only possible case is when 3 is dividing a square, that a square can be in the form of 3m or 3m plus 1. But in this case, 2021 is in the form of 3m plus 2, because the sum of the digits is 5, and 5 can be written as 3m plus 2. So we have proved that there is no integer n such that the sum of the digits of n square is 2021. So I hope you have understood the third question, and now let's go to the fourth question. Okay, show that there is no integer abc such that a square plus b square minus 8c equals to 6. Sorry, solution of question 4. So a square minus plus b square equals to 6 plus 8c. Now, so now if you observe that, um, so okay, fine, send 6 this side. A square minus b square, a square plus b square plus minus 6 equals to 8q. I can write, see, this is the division algorithm. Division algorithm. I can write a square plus b square congruent to 6 mod 8. If you have got it till here, you're done. If you have got it till here, you're done. So I have a square plus b square equals to 6 plus 8q, and a square plus b square equal minus 6 equals to 8q. Then I can write this division algorithm as this: a square plus b square congruent to 6 mod m, And then, so like the previous question, like the previous question 3, so we have considered when the remainder is 3, sorry, we have considered when a square is divided by 3. Now in this case, you need to consider when a square is divided by 8, because we have modulo 8. So from, I think from here you can take here, from here you can take here. So I'm leaving the question for you. And the last question, question 5, it's a really simple question. As you can see, the question 5 is really similar, and I want you to try this. And the question 6, 7, 8, 9, 10, 11 would be in my description. It, come on, you can find this in my description below, in the video description. You'll find it. And thank you guys for watching this video. I hope you have understood the whole congruency well and nice. So afterwards, I hope, there's a handout link also below, so I hope you solve the handout and the homework questions, which are really nice. And thank you.